Good morning, everyone, and welcome to another Quanser Live webinar. This webinar will provide an insight into Quanser's academic applications team and our guiding vision for modern engineering education. It would also provide an overview of teaching courseware for students and instructors, examples to accelerate research and development, as well as thorough user guides and technical manuals to get started with any solution. My name is Michelle Davy, and together with my colleague, Gemma Wang, we will be your hosts and moderators this morning. Today's webinar will be presented by Murtaza Bora. Murtaza is the R&D manager for the academic applications team at Quanser, which develops teaching content and research examples to accompany our systems. Over the last 6 years, Murtaza has been involved in developing flight controllers for our Q drone quad order, autonomous applications for Quanser's self-driving vehicle, the Q car, as well as undergraduate teaching content for the Q arm robot manipulator. He's also represented Quanser globally in workshops, trade shows, planetary talks, and conferences. Murtaza holds a master's in applied science in space mechatronics and a bachelor's in engineering science from the University of Toronto, where he taught a graduate course on manipulative robotics as well.
Good morning. This is not a technical webinar. I'm not really going to talk about Quanser solutions, products, or technology, but something a little more personal to most of us. If you have a standing desk, maybe grab a seat. Who knows, feelings may be stirred as we talk about our academic needs as engineering professionals, our problems as researchers and educators. Let's start here. Take a moment, breathe deep, and think back at the day you knew for sure. The moment a spark was lit and you decided to pursue engineering. When I picked my courses in high school, I was navigating an optimization problem that kept my options open. I was debating pursuing two careers, life sciences going into med school, or as an alternative, pursuing a career. After my parents shot down my writing endeavors, I built a new case for them, a pre-med major in biomedical engineering. Little did they know that my inspiration for this came from a seed planted by a movie. When I think back about this, it's not particularly Tony Stark that inspired me, rich, smart, philanthropic, and popular. It was something else. He solved problems as a mechanic, electrician, roboticist, really as a multidisciplinary engineer. He didn't do it right the first time either. He failed a bunch as he encountered issues and fixed them, with a motivational spark to keep going. The motivation to want to do the same woke something in me that eventually led down a very different career in aerospace, robotics, and education. At the heart of successful modern engineers and their careers is a motivation to solve problems. And no matter what creates that spark, it is important to keep that alive and going, as it has the potential to drive students through their formative educational years on towards the rest of our career, where they themselves will nurture it. That motivational spark, in tandem with our need to solve problems on the frontier of technology, is what drives innovation. The engineering problems themselves, though, have changed as well. They are bigger and sophisticated. Modern engineering problems are inherently complex. At the academic frontier lies cutting-edge research, employing bright minds to solve the sophisticated aspects of our complex industrial problems. Both the industrial and academic research space is backed and fed by a steady stream of bright minds graduating not only with the skills and competencies to solve these problems, but also the multidisciplinary spark to do so and thrive in that field. The spark of motivation carries an engineer through their education, academia, and onto the world of modern engineering. I know it did for myself. So speaking a little bit about me, I'm Murtaza, and 2 years into my undergraduate program at the University of Toronto in engineering science, I followed this up with a master's in space mechatronics from the Institute of Aerospace Studies, while gaining experience as a teaching assistant and tutor in addition to my research. I joined Quanser in the summer of 2016, and over my first 5 years there, I worked on a variety of education and research content for controls and dynamics, aerial, manipulator, and mobile robotics, as well as autonomous and self-driving applications. In April of 2022, I took on the responsibility of managing the academic applications team at Quanser, which creates a wide variety of academic teaching and research content. Today is all about needs and problems. Our problems collectively as academic problems as researchers and educators, and the task at hand that affects the new generation of modern engineers. In the future, we'll talk about Quanser's academic mission and vision, our design philosophy, the academic applications team at Quanser, and finally, our academic content. So let's approach this from the education and teaching side first. The need is established. We want to create a new generation of engineers that are motivated through their education for what lies ahead. How do we keep them motivated? I have come to know quite a few people who have studied engineering, and I've chosen to apply the soft skills gained from it in alternate careers. One aspect of this, of course, is personal preference, but for quite a few, they got demotivated by pressures of rapidly changing technology and corresponding change in skill requirements. So how do you prepare students to work on complex engineering systems in industry? And honestly, I'm leaning more towards robotics, controls, dynamics, mechatronics, but I think the general question still applies. And we want to prepare them while keeping that motivation alive. To address that complexity by building design intuition as opposed to design experience. Design is, in essence, a series of decisions made about components, algorithms, integration options. Engineering design is extremely diverse and varied. Therefore, general rules and best practices are essential. With a widening gap between complex modern systems can successfully create themselves, the need for students to gain intuition so they can make more informed decisions when designing systems independent of their experience will become more and more essential. In my first year at the University of Toronto, our first design project did not involve building something interesting. It was quite the opposite. We were randomly assigned small household electronics and asked to break them apart completely, including testing them for robustness, rigidity, value and cost, build quality, etc. What this gave us was an insight into why some of the design decisions were made for the product specifically, given the features that the product was designed for. Building intuition to give students the ability to make more informed, educated choices will serve them better in the future design work than specific design experience. In industry, engineering design teams are interdisciplinary for practicality, as expertise is not generally and universally applicable. Mechanical, electrical, software, applications, multiple teams can collaborate together on projects. While expertise and specialized experience is valuable, engineering literacy and cross-disciplinary interfacing is mandatory. Interdisciplinary teams need to be able to communicate effectively so that the goals and requirements of the elements of design are accounted for, which is further improved with broad engineering literacy. Modern systems are increasingly complex and interconnected as well. Traditional project-based design approaches can leave an experience gap for students entering capstone and industrial engineering projects. Instead, a scaffolded approach to dissecting complex systems to identify the design decisions made and customize the applications can be far more valuable. Modern engineering systems are often integrated using off-the-shelf components, or in some cases, full devices. These skills are increasingly important as opposed to creating existing solutions manually. Engineering design for robotics and mechatronics is a topic that is based on the design and development of electromechanical systems is inherently practical. However, an academically appropriate level of theoretical rigor is essential to allow students to generalize their skills. Authenticity is critical to student motivation and the context for mechatronic skills. With industrial alignment, project needs don't need to be fantastic, rockets, autonomous cars, etc., as long as the holistic value of that project is clear. Let's take an example. I was in Indonesia in 2019 when I learned about the waste hordes on the beaches of Bali and the volunteers of an organization called 4Ocean, which helped clean it up frequently and manually. Which got me thinking about Boyan Slat, an engineering student who gave up on his education to focus on the ocean cleanup project. As of 2022, its interceptor robots have been deployed in the Dominican Republic, Vietnam, Malaysia, as well as Indonesia, cleaning up the oceans autonomously. Although we cannot expect every single student to give up on their education and try this out, there are ways to incorporate authentic engineering experiences in programs early on. McMaster University has students working on a system of robots towards an application of waste sorting and recycling in the foundational years in general engineering. Authenticity introduces many opportunities for practical applications in a program, including case studies, industrial collaboration, design dissection, guest lectures, etc. For example, consider gaining the essential skills of robotics, connected and autonomous systems by directly working on a lights out smart manufacturing setup, which builds authentic experiences students won't forget. Numerous courses from computer vision, introduction to robotics, networking and communications, manufacturing, that stem from a variety of engineering disciplines, mechanical, electrical, comp-sci, can all have students working on these systems for their programs while developing multidisciplinary engineering personalities. We have talked about why it's important to deliver authentic experiences to create engineers with design intuition that is inherently multidisciplinary. Courses that encourage student collaboration, plant a seed for what these modern engineers are going to do for most of their career, collaborate. In addition to building such passive elements of work culture and traits, it's also vital to expose students to authentic experiences to boost industry relevance. Having these themes across a strong offering of courses that not only complement each other in course topics, but also apply technology in new ways, help generate more aha moments, ultimately working towards keeping that motivational spark alive. It is vital to take these elements into consideration when designing courses brand new, which are far more in number, and that is easier said than done. Something else that has impacted the educational experience for better or worse is the COVID-19 pandemic. With a variety of course delivery options today, such as blended or hybrid labs, it becomes equally important to deliver these courses online while guaranteeing similar learning outcomes and experiences for students. If the course involves hands-on labs using hardware, this becomes increasingly challenging. Now that we have laid the groundwork for why design intuition, literacy, exploration, and authenticity are vital for the new generation of engineers, let's talk about some issues facing the frontiers of research. For a lot of professors, teaching is a side job, sometimes mandatory and based on personal preference, not always enjoyable. Where their heart truly lies is research, which brings its own set of problems. The life of an academic pushing the frontiers of research isn't easy either. Firstly, you have funding uncertainty and funding constraints. Funding models have shifted from core basic funding to ones allocated through competitive mechanisms and proposals, which is a tedious process. Institutional level pressure related to ranking and research team competition puts a premium on researchers that can demonstrate high performance against easily measured indicators, such as citations, articles in highly cited journals, and an ability to attract more research funds. It's also important to validate research, either through publication or hardware testing. There is a lot of debate in the research community when it comes to high impact factor journal publications as a means to measure the performance of research teams. However, despite the hot debates, the trend is still present. At which new doctorate holders are seeking to join the research workforce is higher than the rate at which older doctorate holders are exiting. Research longevity becomes important because that bottlenecks the transition from a postdoctoral researcher to a full research position. Increased competition also makes it vital to sustain the research in new directions while growing the team. And last but not least, tenure. While universities have started offering a variety of non-tenured research positions, a tenured position is still a sign of sustained high performance and a goal that drives everyday motivation for most academics. We actively think about these issues ourselves at Quanser. We have the experience and are willing to collaborate with you in writing grant proposals, for example, offer support navigating the political and research climate at your institution, connect you with other key academics, help with hardware validation, and collaborate with you on publications. Now consider for a moment an ideal scenario where you have secured funding and all the other issues have been solved. You have now lab. Could be in flight systems, robotics, self-driving, you name it. And you decide to build your own, let's say, quadcopter. You and your team will still have to go through numerous stages of development, including hardware design, firmware development, low-level software architectures and APIs, then developing the software to interface with the solution you have designed or sometimes adopted. And then you get to do the research with the goal of publication. Despite all of that, life still happens. Your students graduate, taking the expertise of working with the systems along with them. There are hardware or software issues that require debugging. Sometimes there might be hardware damage that needs repairs and takes downtime. There's also a need for technical assistance, which isn't readily available with open source code if adopted. We've all waited for someone to answer a question on Stack Overflow for a week. There is an established need for collaboration between engineering companies and academic institutions that can provide engineering support, avenues for continuous improvement, training and consultation, which can ultimately help accelerate the pathway straight to research and publication. To summarize, today we have established the need for prioritizing design intuition over design experience, literacy over specialization, exploration over creation, and experiences. We have also talked about taking various factors into account when designing courses, such as industrial relevance and authentic experiences, the need for multidisciplinary collaboration, as well as a cohesiveness across spark. Finally, we've also talked today about key issues that researchers deal with, including funding uncertainties and constraints, pressures of research longevity and tenure, pressure to publish in high impact factor journals, competition at the institution and research team level, etc. Quanser's mission is to partner with universities around the world to develop engineering platforms that accelerate research and transform educational experiences and alleviate some of these concerns. It is our vision to strive to bring theory to life using innovative technologies to inspire and empower insightful discovery for every engineering program in the world. For over 30 years, Quanser has worked closely with educators around the world, helping them prepare the next generation of professionals in controls, mechatronics, robotics, and autonomous systems. We understand how important it is to excite students for all aspects of engineering through hands-on, engaging experimental systems, while maintaining focus on the rigorous understanding of theory and connecting it to authentic real-life scenarios. In the next webinar, we will dive deeper into Quanser's academic mission and vision, including grants and funding proposals, publications, academic consultation, and courseware development. You'll also find out more about the academic applications team and get an insight into how we take the elements of authenticity, design intuition, and multidisciplinary collaboration into account when designing our courseware to accompany our solutions. Finally, you will get numerous examples of our content and how it is structured for deployment in a variety of complementary courses. That brings us to the end of this webinar. If you relate to any of the needs or problems I've talked about today, please reach out to us. You can scan the QR code at the top left with your smartphone to access our website for more information, and you can scan the code at the top right to connect with me directly on LinkedIn and reach out. Thanks for listening, and I'm happy to take any questions.
Thank you, Murtaza. That was a great presentation. As always, Okay, I think we can proceed to the question and answer period. So, if you have any questions, then please submit them through the chat window. So we got two questions so far. So the first one is, you briefly mentioned about support for writing research proposals. Could you provide a bit more information on that?
For sure. We will cover this in more detail in our second webinar. But in the meantime, if you browse to our website, quanser.com, under support pane, you will find more information about grant proposals. We've also done a webinar on this in the past by our Director of Sales, Amir Pasha Javid, which can answer a lot of these questions in more detail. But in the meantime, if you have any questions related to this, feel free to reach out to us after and we can directly give you some of these resources.
Great, thank you. And I think Gemma posted the link on the chat window as well. Um, another question. Yeah, another question we have is a challenge I see with multidisciplinary research teams is a preference for programming languages, which is okay with research teams, but forcing students to focus on one or the other in a course can also be challenging and must be considered in course design. Can you share your thoughts on that?
Thanks for that. I agree with you. It is important to be able to pick programming languages specific to the needs of your research. For example, if I was doing anything related to machine learning, I would lean towards C++ or Python. But it's also a different story, in my opinion, for courses at the undergraduate level, where I believe it's important to separate theory from implementation. I took a course in scientific computing in my undergraduate program in my fourth year, where we had numerous programming assignments due, and our professor gave us options to implement the solutions in C++, Python, or MATLAB, because that course was shared between multiple disciplines with varying backgrounds. We all learned the theory more or less the same way, and regardless of the language we used, we all learned practical implementation skills.
Great, thank you. Are there any other questions? Okay, well, this brings us to the end of our webinar. We would like to thank everyone who attended today. Please visit our website at www.quanser.com and our LinkedIn page to find out more about our systems and upcoming webinars. Have a great day, everybody.
Thank you, everyone.